So we're going to create today a brand new type of function similar to what we did last year when we developed the trig functions and the inverse trig functions and the logarithm functions. So what we have is a function, okay, and we're going to name it capital F of x, and what it's going to be an integral function. And what that means is it's going to start at some number value a that we'll call a. So that's right here. That's where we're going to start it. And we're going to end it at an x value. So the input into this function is the upper limit of integration. So that's where we're going to stop integrating. And because the little f of t, which is this curve right here, all right, is above the x-axis, then that would mean that this integral function would give us the area. All right. So I want to show you what f of x looks like. What f of x, the value of f of x, we're going to start integrating right here, and we're going to sweep across. Now, the t is the value that we're putting into the function. The x represents something different. Okay, so we got to switch variables. This is called a dummy variable because we can't use the same variable. This x represents this x where we stop integrating, whereas this input right here that we normally call x, we need to call it something different. We're going to call it t, because those are the inputs into this function. Okay, so this would be the function heights versus this x is where we stop integrating. So they're different. That's why we have to label them differently. Okay, so if this is a function, that must mean we can take the derivative. Okay, and in order to get the derivative, we need to add h to this, and then we need to take the limit as h approaches 0, which I'm circling right now. Okay, so I'm going to show you f of x plus h. So f of x plus h would go all the way to x and then add h to it. So it's going to go all the way up to here. So again, you're seeing that t because those are the inputs, and then it stops, right? It stops at x plus h. All right? Okay, so this is the integral of f of x from a to x would be this green part, okay? And we are going to add h to that last x value, which would cause it to move over here to the right. All right. So from the animation, we realize that this curve, the name of it is f of x. And then this capital F of x is different than this, than this lowercase f, all right? This f is the function, where this capital F of x represents the area between a and this x value. And from the animation, we see that capital F of x is equal to the integral from this a value to x. And be careful, because really this needs to be a different value. The input to the function is different than this x. This x right here is actually the end point of integration. So that's the right end point where upper limit of integration, we call it. Okay, so this would be f of t dt, because this x is the input into the function, whereas this x is where we stop the integration. Okay, and then you saw that if we go a little bit further and we add h to it, okay, so f of x plus h would be all of this gray area along with this green area. And so f of this new function, f of x plus h, would equal the integral from a to x plus h of f of t dt. All right. So we're going to need this because we are going to talk about if we have this function, right? This new type of function that's an integral function. That's what this is, right? You must be able to take the derivative of it, okay? So this is like a brand new type of function, like when we introduced logarithm functions and the trig functions and the inverse trig functions, okay? So this is a function that accumulates area for us, okay? So what is the derivative? So this brand new type of function, what's the derivative? Well, by the definition of derivative, we know that f, capital F prime of x is equal to the limit as h approaches 0 of capital F of x plus h minus capital F of x over h. And this is simply the definition of a derivative. All right. So for this, instead of dividing by h, I'm going to take this and multiply by 1 over h. And I'm going to modify this, and you're going to see why in just a little bit, okay? So this is equal to the limit as h approaches 0 of 1 over h. And I'm going to use a bracket. And then it's going to be capital F of x plus h minus capital F of x. And what do we know about this? Well, that's this integral right here. And this one is this integral right here. So I'm going to replace these with the integral piece. So this becomes the limit as h approaches 0 of 1 over h times, and this would be the integral from a to x plus h, f of t dt minus, and then the integral from a to x of f of t dt. Okay, so if we're going from a all the way here to x plus h, and we're going to subtract the integral from a to x right here. So this has to do with like the properties of integrals. This one's the whole, right? This integral is all of this area, gray and green. We're going to subtract just the gray. Well, what would we be left with? This actually becomes the integral from x to x plus h, okay, of f of t dt. Okay, so once again, this lowercase f of t is this function. Okay, that's curvy function right here. All right, so this becomes the limit as h approaches 0 of 1 over h times, and then this would be just simply the integral from x to x plus h f of t dt. But this h right here, how can we rewrite h? There's another way to write h. Okay, so I know this x is from here to here. That would be x. From 0 to x, that would be x. And then I also know that from here all the way across to right here would be my x plus h. And then from this x to this x plus h, well, that would just be h, right? So this h right here, we can get by taking x plus h minus this x. So this is, again, this is the whole, right, all the way across, minus this x right here, this x value right here, and what will we be left with is this h. So this right here, okay, gets replaced with the limit as h approaches 0 of 1 over x plus h minus x. So I'm going to write this in parentheses, x plus h minus x times the integral from x to x plus h, f of t dt. This should look familiar to us, okay? Because we did this, this is the lesson. Whoops, I'm sorry. This would be x plus h minus x, integral from x to x plus h, f of t dt. All right, this should look familiar to us. All right, it's the mean value. Okay, this is the mean value of a function. So we can apply the mean value theorem that says if you have 1 over b minus a times the integral from a to b of some function, let's call it f of x dx, there has to be some value in between a and b, all right, some value between a and b where you could put that into the function and it would equal c. All right, so what does that mean? That means this whole piece right here can be replaced with f of c. And so what we're going to take is we're going to take the limit as h approaches 0, and this whole thing gets replaced with f of c. Well, what does f of c become if you squeeze h? So I'm going to go back to the animation and show you what happens as h goes to 0. So what happens when we shrink
h, and we make h go to 0. Well, remember, c is somewhere in between here. I know this animation doesn't have the c, but c is somewhere in between here, right? So as we go to shrink the h, and I'm going to try to shrink it by dragging it, okay? As we shrink it, c is still somewhere in between, somewhere in between, somewhere in between, somewhere in between, somewhere in between. But see, it's somewhere in between, but it's getting closer and closer to being in between here, right? So what happens when it goes to 0? Well, that c value happens to occur right at the end of integration. It doesn't matter if I move this over or not, right? I'm going to move it over. If I shrink my h here, if I shrink my h, the c is somewhere in between x and x plus h. So it's somewhere in between here, And so when you go to shrink h and let h go to 0, that f of c becomes f of x. And this is the height here. This is lowercase f of x, okay?
So from the video, you realize that, okay, as h goes to 0, okay, this is shrinking. This side right here is coming in. And so c is going to be somewhere in between. And as this goes to 0, this c becomes the x. So as h goes to 0, it's sandwiched in between the x and the x plus h, and it gets squeezed to right here, and it's the same as x then. All right, so what does that mean? That means that this is equal to f of x, lowercase f of x. So that means the derivative of our function, of our integral function, is simply the function that we were integrating, the integrand. That's all it is, okay? And so these are gonna be, so this is really kind of powerful. Like when you take the derivative of an integral function, it's just the function you're integrating, all right? Okay, so let's look at some problems. So this is called the fundamental theorem of calculus part 1. And if f is continuous on the closed interval a to b, then the function, this new type of function, which is an integral function, is defined as this, has a derivative at every point x from a to b, okay? And the derivative, right, and this could also be written as f prime of x, is simply f of x. Okay, so this is really beautiful because all you have to do is, if you look at this problem right here, all we're gonna have to do, if we want to find the derivative of this integral function, this is the integral function, and we want to find the derivative of it, all you gotta do is put your x right here for t. And so this becomes 3x plus 5, and we're done. How's that for easy problem, huh? Okay, all right, that's it. That's all you have to do, okay? Now, there is one little itty bitty piece that we got to look at, and that's going to be the next problem. So that's fine and dandy when this is x, right? You just plug it in like we did up here, right? But what if it's not x, okay? So we have to put this x squared into the function right here because that's what happens, okay? That x becomes part of the function that we're integrating. Now, if we're taking the derivative and we're putting a function that's not x in here, we got to take the derivative of this, okay? So what happens is we got to apply the chain rule, all right? So what this looks like is we have, this becomes 3 and the t becomes the x squared, we replace it. So 3x squared plus 5. But now we got to take the derivative of x squared with respect to x. So times the derivative with respect to x of x squared. And so this is going to become simply 3x squared plus 5 times, and the derivative of x squared with respect to x would be 2x. I probably should put parentheses around it. Okay. So basically, we're taking, instead of the derivative d dx, we are taking the derivative of capital F of x squared. Okay, so that becomes, and that's why we're writing it this way, it becomes f prime of x squared times, and then 2x, right? That's how that's how we do it. Okay, that's actually what we're doing right here. Okay, we're gonna do some more of these, okay? So don't worry if you don't quite get it yet. So when we take the derivative with respect to x of this integral function a to g of x, f of t dt, this becomes f of, and we're going to put whatever this function into the function, and then times, and then it's the derivative, because see how it's it's a composition of functions here. Then we got to take the derivative of this, so it'd be times g prime of x. And if this was just x, then when we take the derivative of x, this just becomes 1. So if you always apply this, you're going to be okay. All right. It's just that if this was x, then this is just simply 1. Okay. So for these next 3 examples, this should go fairly quickly. Okay. If we want to take the derivative with respect to x from pi to x, so this is where we're starting the integration. This is the variable that tells us where to stop the integration of this function cosine t dt. So this needs to be a t and a dt. Then this simply becomes cosine of, and we're going to put this x right here. So cosine of x, and that's it. That's the derivative of this integral function. Okay, so this one we're going to take the derivative with respect to x from 0 to x of 1 over 1 plus t squared dt. This simply becomes 1 over 1 plus x squared, and we're done. I mean, the derivative rules for these are really easy. Okay. All right, so now this isn't x squared, or it isn't x, it's x squared, right? So we're gonna have to do this a little bit differently. So this is still gonna be, we're gonna plug x squared in here because that's where we stop the integration. So this is gonna be cosine of x squared, but then we gotta multiply that by the derivative with respect to x of x squared. So this becomes cosine of x squared times, and this just becomes 2x. And that's all there is to it. You may want to rewrite this as 2x cosine of x squared. You could write it that way too, or leave it like this. That'd be fine too. All right. So for this problem right here, our integral function is defined as y equals the integral from x to 5 of 3t sine t dt, and I want to find dy over dx. Now, that derivative that I showed you, the rule for derivative, it has to be from a constant to the x value. So this isn't written correctly, right? But we have a property of integrals that says we can switch this. So what we're going to do is we're going to rewrite this. And so this is y is equal to, and you can switch these as long as you take the negative of it. So y is going to equal negative of the integral. And instead of from x to 5, it's going to be 5 to x. And then 3t sine of t dt. And if we want to find the derivative of this, that would be dy over dx. Okay, so dy over dx is simply going to be equal to negative, and all I got to do is put the x's in here for t and t. So this would be minus 3x sine of x. So to use this derivative rule, we got to start it at a constant. Okay. So for this next one, we got to be a little creative. We have y is equal to the integral from 2x to x squared of 1 over 2 plus e to the t dt, and we want to find dy over dt. Okay, so, or dy over dx, okay? And so what we need to do is we need to break this up, okay? We need to rewrite this because we need a constant. So I'm going to pick a, where a is some constant between 2x and x squared. So I'm going to be able to rewrite this as y is equal to the integral from 2x to some value a of 1 over 2 plus e to the t dt. And I should say this, a is a constant. Okay, and then I'm going to go from a to x squared. So plus the integral from a to x squared of 1 over 2 plus e to the t dt. Okay, so this one's, we could find the derivative right now because this is starting at a constant and we're going to x squared. So this one's ready to go. This one is not. I'm going to have to switch this one. So it's like what we did before. Okay, so this is going to become y is equal to negative the integral. Instead of 2x to a, it's going to be a to 2x. And that's going to allow me to take the derivative of this. So 1 over 2 plus e to the t dt plus, and then the integral from a to x squared, 1 over 2 plus e to the t dt. Okay, so now we can take the derivative of this. So dy over dx, because a is a constant, right, for here and here, this is just going to be, we're going to plug 2x in for my t here. And now this is not x, so I'm going to have to take the derivative of it. So this is minus 1 over 2 plus e to the 2x power times, and I'm going to take the derivative with respect to x of 2x. And to that, I'm going to add, and this would be 1 over 2 plus e to the x squared times the derivative with respect to x of x squared. Okay, so cleaning this up, this becomes dy over dx is equal to, this is just going to be 2, so this is going to be negative 2 over 2 plus e to the 2x. And this is going to be 2x times this fraction, so plus 2x over e, or not e, whoops, 2 plus e to the x squared. So let me fix this. Okay, so 2 plus e to the x squared. And that's fine if you leave your answer just like that, okay? All right, so that's how you do the derivative of these integral functions, okay? So for this next problem, I want to construct a function. So I want to create this integral function, okay, and that satisfies the given condition. So I want, all right, when I take the derivative of this function, I want e to the x tan x, and I want y equal to 5 when x equals 8. Okay, so I want to start this at 8. And one of the things I'm going to use this property that if I integrate from 8 to 8 of f of x dx, I know that's going to come out to be 0. So I'm going to use that to help me get this constant, okay? So the way I'm going to do that is I'm going to let y equal the integral, and I'm going to start it at this x value that I want to put in. So I'm going to go from starting at 8, I'm going to go to x, and this is going to be e, and I can't use e to the x because x is where I stop integrating, right? It's going to be t. So this is going to be e to the t tan of t dt. Now, what happens when I get if I put 8 into this? If I put 8 into this, I want to get 5 out. So the way I can do that is if I put 8 right here, if when x is 8, that's going to be the integral from 8 to 8, and that's going to make this whole integral become 0. So then that allows me to just add 5, because that will force my y to be 5, because I know if I put 8 in here, right, if I integrate from 8 to 8, this whole integral is going to be 0 plus 5, and that's going to give me a y value of 5. So I want this to happen, right? I want to be able to put 8 into this integral function and get out 5. And this is a way to force that to happen, okay? And then when I take the derivative of this, well, what's the derivative of this? Well, it'd be e to the x tan of x, right? And plus the derivative of 5, which is a constant, that'd be 0, okay? So if I took the derivative of this, I would get this function right here. Okay, so really all you have to do is you want to start your integration, whatever x value you have, and you want to add your constant, and this is going to be your constant right here. Okay, so for this next problem, all right, if I want the derivative to be this, and I want it y to equal 4 when x equals -3, all I need to do is use y is equal to the integral, and I want to put -3 in for my x. So I'm going to go from -3 to x, because if I put -3 in here, that's going to be the integral from -3 to -3, which will give me 0. This is the function I'm going to integrate, the square root of 3 minus cosine of x. And I wrote x, and I shouldn't have. You got to be careful on that. It should be t. So cosine of t, okay? Because the t is the input to the function, to this lowercase f of x, and the x is where you stop the integration. So they are different values. That's why we have to use different variables, okay? Now, this is going to be dt. Now, if I integrate this, if I put -3 in here, right, that's going to give me 0. I want it to be 4. So all I need to do is add 4 and I'll have it. And that's all you have to do. Okay. All right. That's all we have for today. All right. So tomorrow's going to be a bigger fundamental theorem of calculus part 2, which is huge. Okay. That's going to be the big part.